here is an important fact about the sun and the stars in general. If we think about stars as ideal black bodies, then we should expect the light that they emit to obey blackbody radiation laws. And if we graph the intensity per unit wavelength as function of wavelength for the sun, we expect this kind of curve, this kind of brightness per unit wavelength. And we should expect a peak in the visible part of the spectrum. However, this disregards an important reality. Stars have an atmosphere. This is not only true for the sun, this is true for all the stars. They have an extended atmosphere. In fact, it's thousands of kilometers thick. So when the light that comes out of the surface of the star, which obeys the radiation law of black bodies, passes through the atmosphere, some photons are intercepted by the electrons of the atoms in the atmosphere. So these electrons would absorb some specific photons, gain energy in the process of that absorption. And so the light that reaches the Earth is missing some of those photons that have been absorbed. So if the atmosphere contains hydrogen, then hydrogen lines will be missing. If the atmosphere contains helium, then helium lines will be missing. And in fact, what we'll see is that most of the elements of the periodic table are present in the atmosphere and therefore will contribute to absorption lines. So when we observe direct light from the sun and we pass that light through a spectroscope and we separate the wavelengths of light emitted by the sun from red to violet, we would see the continuous spectrum of the black body. But in addition, we would see a large number of darker, narrow areas. These darker lines correspond to specific wavelengths that have been absorbed by the electrons in the atmosphere of the sun. And there are thousands of these lines, from hydrogen, from helium, from carbon, from oxygen, from all the elements. And so the real spectrum of the sun is that of a black body minus a bunch of absorption lines that correspond to all the elements. But when electrons absorb photons and gain energy levels, eventually they will go back to the ground state. And by doing so, they will re-emit those photons. However, the photons being absorbed, so if we look at the direct light from the sun, then we see a black body minus the photons that have been absorbed. However, once they are re-emitted, so later on when the electrons return to the ground state, they get re-emitted in random directions. These are these arrows that you see here, being re-emitted in random direction. Some of these directions is towards you, but most of it is elsewhere. So when you look at the light directly from the sun, you're going to be seeing a lot of absorption and very little of it returning to you. However, if you were to somehow block the light from the sun, you block the direct light, so that the only thing you would see is the atmosphere around it. And then what you would see is the faint light being re-emitted by the electrons. So this happens during a solar eclipse. When the moon blocks the sun, what you can see is the atmosphere of the sun all around. And that atmosphere is the spectrum of light from that atmosphere is an emission spectrum like this. You would see only the bright wavelengths that correspond to the wavelengths of light re-emitted by the electrons as they jump down. So you would see lines of hydrogen and helium and carbon and all the other elements. But this is an exceptional thing to see. It only happens during the eclipse. For the most part, when we look directly at the light from the sun or from other stars, and we analyze that light with a spectrometer, we see a blackbody radiation minus absorption line. So we see an absorption spectrum. And there is a lot we can learn from it, starting by composition. So we identify the elements present, but there are actually many other things, and there is an entire chapter dedicated to the spectroscopy and its use to study the sun and the stars.